So, wait a second, where's the pointer? Ah, here. Okay. So, this is, again, joint work with quite a few people in different places, including one of the organizers, but actually I won't have the time to talk about all the things that we did with all the people here. I will concentrate on certain things, obviously. And so the motivation is that the system, the climate system, is highly nonlinear and quite complex. That's what's called in the United States motherhood and apple pie. You know, you find these words in the introductions to the IPCC reports and to various chapters, and then they are promptly forgotten. The system's major components, the atmosphere, oceans, ice sheets, etc., evolve on many time and space scales. The predictive understanding is one of the few useful things which I learned in serving many, many years on committees, on panels, and so on of the National Research Council. Predictive understanding is what you say when you want money from the government. Okay? People say that it's hard to predict. You know, Mark Twain said it's hard to predict, especially the future. It's actually not hard to predict at all. What is hard is to believe the predictions. Okay? And that's why you need the understanding. No amount of statistical modeling will give you the kind of confidence that understanding what is causing the phenomena does. So predictive understanding has to rely on the system's physical, chemical, biological modelings, so all those details, but also on the thorough mathematical analysis of the models as obtained, the forest versus the trees. The hierarchical modeling approach allows one to give proper weight to the understanding provided by the models versus their realism. Back and forth between toy or conceptual models and detailed, again in quotation mark, realistic models. Why do I put these in quotation marks? Well, simple models are looked down upon because they're simple. Okay? But actually, Ed Lorenz, I mean, I didn't hear him say this himself, but it's been cited to me, once said that if you had an atmospheric GCM which did exactly what the atmosphere does, it would be totally useless, because you wouldn't understand it any better than the atmosphere. Okay? Now that's not quite true, because in the model you can change the parameters, which in nature you cannot, or at least you shouldn't. Actually, we are. But we can't do this, you know, with very many parameter values in a systematic way. So, you know, toy, it's actually for people who practice it a proud term, because I think that Einstein said that everything should be made as simple as possible, but of course not any simpler. Why do I put in quotation marks here realistic for these things that are called GCMs, interpreted either as general circulation models or more recently as global climate models, same acronym? How many parameters do you think a GCM has? You know, a GCM is clearly something semi-empirical. It's not like the Schrödinger equations or the Maxwell equations. There are lots of things, clouds and stuff. So how many parameters do you think, you know, Roberto Mechoso has talked about parameters. How many parameters do you think a realistic model has? 1, 2, 10, 100? No. A good 100. And now finally, you know, previously large groups around these GCMs just used to work by trial and error. You change this parameterization, it fixed something, but it deteriorated something else. Now people are starting to look at the sensitivity of these models to parameter changes in a more systematic way. And 2 or 3 groups in Britain, at Livermore, you know, somewhere else, basically decided that out of these 100 plus parameters, I can't say independently because obviously they talk to each other, but they decided that the good 30 are really, really important. Now, if you get up in the morning and tune your stereo, you only have to tune one parameter, the frequency of the station. You imagine what it would be to have to tune 30 parameters. Again, anybody who knows about optimization knows that beyond a few parameters, you have the surface of the moon, you have lots of local minima. It's very, very complicated. So, realism is in the eye of the beholder. Clearly, you have to go back and forth, not just between simple and more detailed models, but also between models and data. That was much of the point of George's first few slides. So, to me, clouds are terribly important, but another thing that is terribly important is how do we disentangle natural variability from the anthropogenic forcing? Can we and should we or not? So since somebody quoted Galileo, I did find last night the quote both in the original Italian and in translation. Philosophy is written in, incidentally, George, there are some of us birds who are interested in ornithology, So philosophy is written in this grand book, the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. Now, the characters in Galileo's time were a little bit different from the characters that we use today, but the concept is basically there. Okay, so climate and its sensitivity. Let's say CO2 doubles. How will climate change? So basically, the thinking of the hundreds and hundreds of people who work on the IPCC successive assessment reports is equilibrium sensitivity. So it is this upper panel. Here is time. Here is global average temperature, say CO2 content. There are other things, but this is the essence of it. You have a certain CO2 level. You have a certain equilibrium climate. Okay? And then you change the CO2, so will the equilibrium temperature. So climate in a stable equilibrium in language of dynamical systems fixed point. If so, temperature will just shift gradually to its new equilibrium value. If you do this, slowly rather than by a jump, it's still the same thing. Let's just say that climate is purely periodic. Let's say, for instance, that ENSO, the El Niño Southern Oscillation, would be purely periodic. And so now the picture is this. It's true that the mean will go up. The fact that you have variability is very unlikely to change that. The mean will go up, but now there are other things that can change. The period, the amplitude, the phase of this periodic solution, which again in the language of dynamical systems is called the limit cycle. Now here I say, how about some real stuff? Now, chaotic plus random. Now I don't have a good figure for that. It looks pretty much like this, except it has higher amplitude, but you can put the irregularities on it. So the real problem of climate change is not this, it is that. And that's what I'm trying to talk about today. Okay, so I will start again with just a little bit of motivation. The IPCC... Yeah?
Could you give a definition what is climate sensitivity?
I will by the end of this lecture.
Okay.
That's what I'm doing. Okay, remember the title of this lecture. Okay, the title of this lecture is Toward a Mathematical Theory of Climate Sensitivity. Okay?
But
so,
generally, what is climate sensitivity?
well, can you wait till the end of the lecture? I can't.
It would be nice to give us a hint.
Well, the hint is how does climate in this sense, in other words, not just the mean and the variance, but also things like extreme events change as parameters change. Okay? That's what I mean by climate sensitivity. Okay? Okay, thank you for asking the right question. Okay, so I'll start with the IPCC process results and uncertainties. Natural climate variability is a source of uncertainties. I don't know whether it's bigger than clouds or less, but it's certainly something that is less studied or has been less studied than clouds. So sensitivity to initial data, this is something that we've sort of understood. Sensitivity to model formulation is what we're talking about today. So uncertainties and how to fix them. I will talk a little bit about structural stability and other kinds of robustness. I will tell you what structural stability is. But just think in general that you would like to have a model that is robust to a large class of changes. And then I will try to tell you that we've been barking up the wrong tree. Okay? In other words, we've been thinking about closed systems which are defined mathematically as autonomous, and climate is, the Earth's climate system is clearly not closed, and it is clearly not modeled well by an autonomous system that might be good for weather, but not for long-term climate. I'll use two illustrative examples. The one that everybody uses, the Lorentz convection model. If I have I have reserved transparencies for an ENSO model, and it has some interesting results, but I might not have the time. Sorry. Then I'll introduce what's called linear response theory and climate sensitivity in this perspective, and end with conclusions and references. So natural variability and anthropogenic forcing. I call this a grand unification because I've asked to speak to physicists. And if you speak to physicists, including people in the room who are Nobel laureates, it has to be grand, otherwise they don't pay any attention. Okay? And some selected bibliography. Okay, so much, if not all of this, started with these observations where the colleague now passed away from Scripps, David Keeling, who put this station on Mauna Loa, which is the Earth point pretty much most farthest away from all other land, to measure CO2 concentrations. And here is another trace like that from the South Pole. There are, of course, more recent records. The reason I like to show this is because basically, on the one hand, of course, it shows, as I say, what motivated much of this, the constant increase in CO2 concentrations and other trace gases. But it shows two other things. One is that there's this up and down. Anybody knows what that up and down is? Of course, the people who know shouldn't really guess. Yeah, it's a seasonal cycle. And it's basically what you're watching is the planet breathing. Okay? It inhales in summer and it exhales in winter. But then you'll tell me, yes, but we learned in kindergarten that there are two hemispheres, summer in the one when it's winter in the other. Okay? Well, this has to do with the fact that there's much more photosynthesis in the northern hemisphere because there's more land. The ocean only breathes, if you wish, along narrow upwelling zones. Okay? So you watch essentially the northern hemisphere breathing. And then how about this thing at the South Pole? You see that the amplitude is much smaller but non-zero. This tells you without doing any computation that essentially the mixing time of the atmosphere is about a year. Okay? So now here, temperature and greenhouse gases. Greenhouse gases go up, temperatures go up. It's got to do with us at least a bit, doesn't it? But it's actually much more complicated because you saw that at least CO2, which is the most important greenhouse gas after water vapor, which is naturally occurring, etc. Okay, it's the most important trace greenhouse gas, if you wish. Okay, is going up somewhat exponentially. A back of the envelope molecular spectroscopy computation tells you that the temperature should be going up linearly. Does the temperature go up linearly? No, it doesn't. Okay, so there's other stuff going on. Okay, so
why did you conclude that the mixing time is one year?
Well, because if it were much longer, then you wouldn't see anything at the South Pole, and if it were much shorter, then the amplitude would be pretty much the same as at Mauna Loa. Okay,
Several years, not
well, I mean, order of magnitude compared to 1,000 years. Okay. For the ocean, it's 100 or somewhere between 100 and 1,000 years. Again, chemical oceanographers change their mind about that from time to time. But
not one.
no, it's not one exactly. I'm just saying order of one as opposed to 100. Okay? Okay, thanks for being still awake. Okay, so actually, this diagram, which eventually I put into an encyclopedia article, was supposed at one point to be, the National Research Council organizes in each area of science every 10 years a review of the field. And quite a few years ago, John Dutton chaired one of these efforts. And he wanted to put it into that report, but it was too controversial. Okay? Why is this controversial? Because it shows simply schematically that, it should be going up linearly if it were really just greenhouse gases, and it doesn't. So, I say here, unfortunately, things aren't that easy. So, it got to do with us at least a bit, doesn't it? But it's not what to do. Try to achieve better interpretation of an agreement between models, and between models and data, of course. So it's a natural variability that introduces additional complexity. So it's a network of feedbacks that George was talking about. into the anthropogenic climate change problem. The most common interpretation of observations and GCM simulations, so you have one of these really big machineries which takes 10 years to develop and many months to run, and then you interpret it in terms of a scalar linear ordinary differential equation. Okay? This was essentially what the first 3 assessment reports of the IPCC did. The equation is C, time derivative of global temperatures minus KT plus Q. K is a sum of feedbacks, both positive and negative. Q is a sum of sources and sinks, which might change in time. As a matter of fact, I think that the first report at least was organized by the expertise of various people into a particular feedback or source and sink. Okay? So clearly, because of this complexity, we need to consider instead, and the big progress in the 4th assessment report was that so-called fingerprinting was introduced. So instead of having a linear scalar ODE, you now think of a linear PDE, if you wish, at best. So instead what we need to do, consider a system of nonlinear partial differential equations, which parameters, and with forcing, which is both additive and multiplicative, both deterministic and stochastic. And of course, since people here came to a workshop on mathematics and climate, I hope that that doesn't look too strange to you. Okay, next, how many people have seen this diagram? Yeah, many. Okay, so for those who haven't, this is, since there are all these hundreds of people who work on this, you need a lot of acronyms. So IPCC is the intergovernmental, not international, intergovernmental panel on climate change, which was dictated by Rio 20 years ago. AR4 is the 4th assessment report. WG1, not I, is a working group 1, the one that deals with physical phenomena. And SPM is summary for policymakers, so that's what the press gets to see. Policymakers sort of don't care, but anyhow, it's called that. So the different colors indicate different scenarios of how we will be behaving or misbehaving. Okay, the yellow one is if we behave very nicely, if we listen to Graciela and Eugenia and lots of other people who tell us that we should be doing this, and it would be nice to do this. This is if we just keep doing what we're doing, and in between there's some partial attempts at behaving a little bit better. Now, for each one of these scenarios, the 20 or so models that participated in the 20th report, in the 4th assessment report, this is the range of global temperatures. Okay? Now, this has not been reduced since the report about 30 years ago, headed by Charney of the National Research Council, which talked for the first time, about the effect, collectively, as an academy statement, about the effect of greenhouse gases on temperature. So at that time, it said for period doubling, if you just do this, the range of temperatures will be 1.5 to 4.5 degrees. So that's 3 degrees range. Okay, in the meantime, we don't do just doubling, we do these projections, with gradually changing temperatures, but the difference is still tends to increase rather than decrease, actually. And there are reasons for that. And, well, we can discuss them at the end. So, natural climate variability is a source of uncertainty, sensitivity to initial data versus sensitivity to model formulation. So, sensitivity to initial data is what Eugenia talked about, wonderfully yesterday. This is from Tim Palmer, who was her competitor at the European Center when she was at NMC, and I just happen to have this handy. This is the 50 members of an ensemble of forecast for a particular strong storm in the extratropical cyclone in the northern hemisphere, which happened to hit Paris at the time when I was on sabbatical there, and blew off the roof of the office next to mine. Okay, the storm was called Lothar. What is shown here is the deterministic prediction. Again, I refer you to Eugenia's talk. This is the verification. Again, this is 500 millibar contours. Okay, so 500 millibar is roughly the middle of the atmosphere where vertical velocities on suitable averages are roughly 0. Okay, so it represents essentially the motion of the atmosphere. And you see here that some of the forecasts are perfectly flat. So this is the storm, you know. Some of them have the storm. Some of them actually have it stronger than it occurred. Okay? But in any case, there is a fanning out of trajectories, which is not truly exponential divergence as we're usually taught in dynamical systems. It is somewhat bimodal. It tends to be either this or that. Okay? So this is well captured, again, metaphorically by the Lorentz model. This is out of Lenny Smith's contribution to Encyclopedia of Atmospheric Sciences, a previous edition. Roberto mentioned the second edition, which is coming out. So, you know, the classical view of dynamical system theory is positive Lyapunov exponent trajectories diverge exponentially uniformly, but actually the presence of multiple regimes gives you what's sometimes called coarse graining, a much more structured behavior in phase space. So still the probability distribution function of PDF, when calculated forward in time, is pretty smeared out. So we sort of lose track of where things are. This is also out of that summary for policymakers. So what's it going to be like by 2100? So these are things that, like the phenomenon and direction of the trend, warmer and fewer cold days and nights over most land areas, etc. Warm spells, heat waves, and here likelihood the trend occurred in late 20th century, typically post-1960. So this, for instance, is very likely. Likelihood of a human contribution to observed trend, likelihood of future trends based on projection for using these scenarios. And here is one that I really love, more likely than not. In other words, if you flipped a coin or you ran 20 GCMs, the result would be pretty much the same. Okay?
60% instead of 50%.
Well, okay, a slightly biased coin. Okay? Okay, so now to how to fix them. Structural stability and other kinds of robustness and non-autonomous. So this is another one that I have from Lenny. You know, clearly we meet at a lot of meetings, and I like his slides. The UK Met Office has a website on which you can go and put your zip code and look at the mean temperature for your district for the last 5 years of this century, or any other 5 years in this century. If this is not ridiculous, I don't know what is, but you have such a website, no matter what Lenny tried to tell, you know, the media. And furthermore, they have estimates of the different sources of uncertainty. Okay, so this is like the clouds in global change. Okay, internal variability, carbon cycle, structural uncertainty. I don't know what they mean by structural uncertainty. Maybe they mean the same thing as dynamical systems. Parameter uncertainty, downscaling. So, you know, it's with 2 digits. This is 24, this is 22, 19. This happens to be, you know, according to Lenny, much larger than 19. Okay, so, you know, this is just to tell you why some people get irritated by the bandwagon. Okay? So, can we nonlinear dynamicists help? This is a picture. This is the dream of structural stability of differentiable dynamical systems from the classical book of Abraham and Maston quite a while ago. So the hope was, you know, there are certain simple systems, essentially those which are, well, they're called axiom A. They're essentially hyperbolic. Basically, the stable and unstable manifolds are perpendicular to each other. There are no degeneracies. Okay? So those are structurally stable. This is a concept introduced by a physicist and a mathematician, Andronov and Pontryagin. Between the two wars, they basically said for a model to be physically useful, it should be robust, and they defined this concept of structural stability, which is a certain kind of topological robustness, which is maybe not the most useful one for our problem. But in any case, the dream that all systems would be this clearly crumbled. I mean, even something as simple as a Lorentz system is not structurally stable because it has this singularity at the origin. You know, there are so-called homoclinic cycles which go off as unstable and come back as stable. So we need to do something else. Furthermore, as I said, you know, we have sort of understood, I mean, it took about 20 or 30 years to understand what the Lorentz model does. You know, I mean, again, Eugenia pointed out the role of her colleague Jim York in bringing this to the attention of other people. And, but it might be good for weather prediction, but it is not good for climate. Because there are parameters that change in time, like greenhouse gas concentration, and there's forcing that changes in time, like solar forcing, seasons, etc. So what do you do about a non-autonomous dynamical system? Again, start with something very simple in order to explain this concept of pullback attraction. Consider the scalar linear ODE like the one that I showed you earlier, x dot minus alpha x plus sigma t, alpha and sigma positive. Look at the autonomous part of this ODE, x dot minus alpha x. So again, alpha is positive. Everything converges to 0. Okay? Fine. You're done. There's a fixed point. Now, what happens if I have sigma non-zero larger than 0 in particular? Let's say that I want to know what happens to the system at this time t. This is the time at which I observe it, say, now. Well, what I have to do is to pull back into the far past and start a bunch of trajectories which will converge towards this point. And if I do this here, again, I have to pull back. And basically, what I observe that as I move forward in time, this convergence occurs along this straight line, which in this simple case is given in closed form. Okay? So this is the pullback attractor. So this is itself a dynamical object. I mean, the strange attractor of Lorentz was strange, but it's a fixed object in time. Okay? It's more complicated than a fixed point or a limit cycle. It has all sorts of marvelous properties, but it's fixed in time. This one is not, because it needs to describe something for which the forcing or other things change in time. Parameters change in time. So basically, we've shown that a solution at time t started at time s in the past, so the time s in the past from which we started, tends to converge to this object as s tends to minus infinity for every fixed t and for all initial data. So this is pullback attraction, and it depends on dissipativity. The fact that alpha is positive corresponds in a much more complicated system to the system being dissipative. We know that the climate system is dissipative because there are those terms in the equations for the atmosphere, oceans, etc. So this is the right thing. What does it mean physically?
Can you say again what S is?
Pardon me?
S.
S is the time, is this, S1, S2. Okay? It's a time to which I have pulled back, and if I let this tend to infinity, this will, these things will tend to exactly the point on the straight line. Okay? So, at time t, for a system starting, now, of course, how in practice, numerically, as you will see, how far back you have to pull depends on how strongly the dissipativity is. And it turns out for all sorts of nice things, you don't have to pull back very far. So the asymptotic regime evolves with time. It's a dynamical object. Dissipation now leads to a dynamic object rather than a static one, like the strange attractor of some autonomous system. So this is essentially the theory of random dynamical systems, RDS rather than DDS, differentiable dynamical systems. It's a counterpart of randomly forced systems of the so-called geometric theory of ODEs. Okay? It allows one to treat things like stochastic differential equations and other more general systems driven by noise as flows. So in the autonomous case, you were just looking at phase space. Here you are looking at phase space time probability space, and the analogies are SD to OD, RD to DDS. This is Ludwig Arnold, no relationship, who wrote a book on this random dynamical system in 1988. To V.I. Arnold, who was one of the people who was not only a great contributor, but also a great expositor of DDS, of differentiable dynamical system. The differentiable dynamical system, the onset are smooth. Okay? So now, a random attractor most generally, where A stands for attractor and omega for the realization of the noise, is both invariant and pullback attracting. So again, just using the figure here, this is a probability space cap omega in which the little omega evolves. And this is the attractor, and these are the things to which you pull back and which flow onto the attractor. So instead of having just a straight line, you know, let's say this is time t, and I'm looking at the so-called fiber of the phase space cap x times the realization. For this to be a good random dynamical system, it has to have a property, okay, I skipped that. It has to have the so-called co-cycle property. It basically says that if you go from here to there and from there to there, it's the same as going from here to there. It's what's called otherwise in, you know, the semigroup property for differentiable operators. Okay, two illustrative examples. So again, the one that I will have the time for is the Lorentz convection model. We'll see if we can still deal with the other one in the question period maybe. Okay, so we didn't make up this theory. This theory has been around for a couple of decades, but frankly, you know, Ludwig Arnold's book is not easy to read even for a well-trained mathematician. So we did a couple things, one of which was to try to explain this to people not in the street, but in rooms like this. So there are a couple of review papers that I will give you in the bibliography. The only thing that was available numerically when we started getting interested in this about 5 or 6 years ago was a picture which is not as good as this by a German mathematician, Schmalfuß, in the Zeitung für angewandte Mathematik or something like that. I forget the exact reference. And basically, this is a snapshot of the random attractor for the Lorentz model. Okay? So RA stands for random attractor. So compute a fixed time t, and for the same realization omega by starting quite a few points in the past, as I said, pulling back. Made up of points transported by the stochastic flow from the remote past. Okay? We use multiplicative noise in the usual deterministic Lorentz model with the classical parameter values for which it's known to be chaotic. As a matter of fact, you know, just for those of you who are not mathematicians, you know, the fact that the Lorentz model, the actual ODE model, not the so-called geometric model of Guggenheim and Williams, has a strange attractor has only been proven fairly recently. So that's why, you know, sometimes doing the mathematics right takes a long time. But, you know, none of us really doubted that that was the case. So here's multiplicative noise for these classical parameter values. So I'm going to show you some of these statistics. So, you know, the point of the approach here, what we call the pathwise approach, is that we're not just looking at the PDF, okay? In the forward approach, what you're looking at is this, okay? These are just at every time, this is the PDF. We are actually looking at the trajectories, at the realizations of the noise. So here is one such realization. So one calls these invariant measures, so-called sample measures for a certain little omega. And for a certain, we compute the probability measure, some fixed time for a fixed realization. We show a projection onto the xz plane with multiplicative noise given like this. So x1, x2, x3 is xyz in the usual notation. W is a Wiener process, so this is white noise. Okay, dW is white noise in common parlance. And so this is the corresponding xi, and the parameter alpha now indicates the multiplicator of this multiplicative noise. This took 10 million points for this picture. And any resemblance to what some of you who know dynamical systems might recognize that the other Arnold's cat map is a pure coincidence to the best of our knowledge. If it is not, it will be very interesting. Now here's another one. This is 1 billion ID, and alpha is equal to 0.5. So this is not small forcing, okay? We do this for forcing, which is comparable. Why do I say it's not small? Because the Lorentz attractor, you know, in this direction it's bigger, but in these directions it's roughly order 1. Okay? So this is pretty amazing. Now, But these are still just frozen statistics at time t. How do they evolve in time? So let's see whether I can do this. Okay. Where is the movie? Okay. Ilya, I think I need help. Okay. I don't know which one is the movie here.
Should I just shoot?
Yeah, just. Okay, so let's see what I can. Yeah, I don't want to magnify it because I don't want to do anything wrong. And now, well, first of all, this is pretty damn amazing. I mean, you know, it's pulling faces at you, and it's doing something which is pretty surprising. You know, the forward PDF is just going to do what it's going to do. Is it, instead of having the onion skin structure of the strange attractor, it will put a PDF which, can you start it again? It will just put a PDF which is concentrated in the middle and dies out at the end. But this, you know, you see that there are two things which are happening. One is that basically the density, the invariant measure, is carried along by the nonlinear deterministic dynamics, and the other one is that there's a jiggle of all of this, which is just the noise. Okay, thank you very much. Let's go back to the... lower resolution, shorter version of this movie exists as supplementary information in one of those two papers that I was referring to. You know, you can actually go there and look at it. Okay, thank you very much, William. Okay, so this is, let's say, a day in the life of the Lorentz model random attractor. So the reference is Chacon, Simonet, and Ghil 2011, Physica D. Okay, now, linear response, coming back to climate sensitivity. I really needed to show you, you know, what we're talking about, so let's come back to climate sensitivity. Okay, so I'm just reminding you of this picture. So now we're well equipped to deal with the real stuff, which includes deterministically chaotic and plus random. Okay? So again, this is the classical picture, the classical strange attractor, physically closed system, model mathematically as an autonomous system. You don't have forcing either deterministic, which you can think of as the anthropogenic forcing. I don't know whether humanity is behaving really deterministically, but let's say. Nor random, think of volcanic eruptions and all sorts of, you know, clouds doing their thing and so on. The attractor is strange, but still fixed in time. So I'm saying by analogy, you know, we don't like things which are unfamiliar. So, you know, our ancestors started with natural numbers, you know, positive integers, and then integers, and then rational numbers, you know, fractions. And then when they found out about square roots and so on, they called those irrational, okay? So let's say that a strange attractor is like an irrational number. So in this interpretation, climate sensitivity is the change in average value, first moment, of the coordinates as a parameter lambda changes. Now, what about the random attractor? Physically open system, model mathematically is non-autonomous, allows for deterministic as well as random forcing. So anthropogenic plus natural if you wish. The attractor is pullback, evolves in time, so it's something more like an imaginary or complex number where you get an extra dimension with respect to the irrational numbers. So climate change, so these are just snapshots from the evolution in that movie that I showed you, okay, going like this. Climate sensitivity is now the change in statistical properties, not just first, but higher order moments of the attractor as one or more parameters change. So again, you know, high order moments can include things like extreme events and so on that, you know, everybody today realizes that nobody really cares about global temperature per se. You know, we don't live smeared out on the globe. So we are really concerned about events that touch us. Okay, so now parameter dependence. So now I'm going from this toy model to what's called, in the hierarchy of models, a so-called intermediate coupled model for ENSO. So this is the Jin, Nilin, and Ghil, you know, Science 94, Physica D 96 model. And this is just a piece of trajectory. Delta is one of the parameters of this model, which deals essentially with the depth of the well-mixed upper layer. And so now this is skewness and this is kurtosis, so third and fourth moment, as a function of changes in this parameter. So this is actually still work in progress, given to me by Mikhail Shekrun. So first of all, you see that here things change on a very fine scale. You see that the change can be smooth, or if there can be jumps, or it can be rough. And the kurtosis and the skewness are smooth or rough in the same places. Okay? So this is not just a coincidence. Now, to study this more fully, we go to another model, which is infinitely dimensional because it's what's called the neutral delay differential equation model. This is a model for the tropical temperature with two delays, okay, so tropical temperature and the depth of the mixed layer as a function of two delays, and including, so in this case the forcing is not random, it's simply the seasonal cycle, okay, given in this way, so mu is given in this way. And the pullback attractant, its invariant measures were computed, and again, what we're looking now is changes in the mean, second, fourth moment, and the fourth panel is something which is becoming very popular these days, which is called, for some reason, the Wasserstein distance, although it was actually started by Gaspard Monge, who was an officer in Napoleon's armies and also a founder of the École Polytechnique in Paris about 200 years ago. And he was sort of interested in how much work it took for the, say, for the soldiers of a platoon to, after digging a trench, to move the earth to another trench nearby. Okay? So it's also called the earth mover's distance. So this is the distance now that you have to move the invariant, the sample measure, as a parameter changes. So you see again that there are intervals of smooth and rough dependence, and they are the same in all four panels. They occur over the same intervals. So now I'm getting to the definition of climate sensitivity, not just in words, but in a mathematical formula. Okay? So this invariant sample measure is plotted here in a 3D perspective. So this is h, the depth of the thermocline, versus h at time t plus 1. And you see that this is very highly concentrated and quite irregular. So essentially, we are looking at this earth mover's distance between one such configuration at a given parameter value and another one at a different set of values. So again, as I said, it's proportional to the work needed to move the total probability mass from one configuration to the other. And you define now, instead of defining climate sensitivity as it was defined before, as a derivative of the mean temperature with respect to one parameter, say mu, you define it as a derivative. So this is no longer a scalar. It's the derivative of this Wasserstein distance at a particular invariant measure with respect to a parameter, which in this case is tau for one of those delays. Now what about, quote unquote, some real stuff in the sense of a big model? So this is work done by these other colleagues, Annalisa Bracco, David Neeland, one of Annalisa's associates at Georgia Tech, and one of David's associates at UCLA, published in PNAS a few years ago. So they took not all of those 30 parameters that I told you was really important, but just some of them. So the idea now is, let's say this is a gustiness parameter in meters per second. So this is something that says how gusty the wind is on subgrid scales. And this is a viscosity time scale, which is the effective lateral or horizontal viscosity. Now, the first thing that you observe is that this is a factor of 2. So this is the range that the authors decided, the range of uncertainty in this parameter for their model at the given resolution. Incidentally, the model is the so-called speedy model of the ICTP. As Annalisa pointed out, when they were calling it speedy, nobody took it seriously. So now they call it the atmospheric GCM of the ICTP. And now it is taken seriously, and there are quite a few papers on using this for monsoons and various other things. So it's a you know, it's not the most highly resolved and most detailed GCM, but it is a GCM. Okay? So this is the reasonable range, and here the factor is 6. So those are uncertainties perceived by the authors to be plausible. Now, the thing is that, as I told you, and as actually George told you, you can't run a GCM like this for very many parameter values, especially if you need to run it for a pretty long time. So you get certain points, and then you fit to those points something that is variously called a meta-model or a response surface or an emulator. There's, the British group calls it an emulator, and I think the Livermore group calls it a response surface, and we at UCLA call it a meta-model, which is, I think, the most general concept. So you fit a meta-model. Actually, there are 2 of these here. There's a linear one in green and a quadratic one in blue. Now, the first thing that happens is that you get a minimum. So this is what the community these days calls a metric, okay? So you get a minimum within the interval which you thought was reasonable. But quite often the minimum is on the boundary. So this says that you had no clue what, in spite of the fact that this is a factor of 6, it is still, the minimum is still outside that interval. So you've learned something. Okay? Now, even in order to do this, you need an efficient optimization algorithm. And again, I don't have the time to go into this, but please read the paper. And there's a follow-up paper that is in press on which Annalisa is lead author. So they use multi-objective algorithms, and they use pretty efficient scanning methods in order to, so, you know, the multi-objective, these are the different things for which they are trying to minimize versus observations, precipitation, temperature at 200 millibar, velocity components, etc., near the surface, mean surface layer pressure, sea level pressure, etc. Okay? So, you know, we are trying to take the stuff that we learned from the simple models and the intermediate ones to the really big ones. Okay, conclusions and references, natural variability and anthropogenic forcing, and okay. Concluding remarks, first one, random dynamical systems and random attractors. A change of paradigm from closed autonomous systems to open non-autonomous ones, and I use a paradigm word advisedly in the sense as it was defined by Thomas Kuhn. You know, a change of paradigm is when you no longer can proceed with the previous ideas, and you have to get some new ones in order to explain the evidence. It's change from closed autonomous to open non-autonomous ones. Random attractors, I hope I convinced you with a little video, are spectacular. I hope also I showed you by the various connections that they're useful, and they're certainly just starting to be explored for climate applications. Actually, just starting to be explored for any applications, because, as I said, there wasn't much numerical work before we did these things. There was a lot of very interesting, rigorous mathematical work, very difficult and very beautiful. Work in progress, study the effects of specific stochastic parameterizations on model robustness. So, you know, Arakawa already was aware decades ago when he used the expression cloud ensemble that in some sense this should be treated stochastically. But in practice, parameterizations have been deterministic. So what's a parameterization? Again, reminding you of something that Roberto said, you know, it's trying to give you the net effect of what happens at subgrid scales on the grid scale. So, you know, these were deterministic, which clearly isn't right. So people have started to do stochastic parameterizations. But again, they've done them piecemeal. You know, you do a stochastic parameterization, you check how it improves something, you know, for instance, the kinetic energy of your model. Okay? The jets are too strong or too weak, and now the jets are about right. But you don't know what it does to the monsoons. Okay? So we want to study the effect of specific stochastic parameterization model robustness, applications to intermediate models and GCMs, implications for climate sensitivity, and for predictability. So again, that would require me to show the 3 slides that I have on the ENSO model, but we'll postpone that for discussion period. So anyhow, Just to remind you, so basically there was this dichotomy in the community. You know, this was not quite as acrimonious an argument as between climate change affirmers and deniers, but the thing that these two approaches to climate science have been sort of pretty hotly debated. So one is, you know, climate is deterministic and autonomous but highly nonlinear, trajectories diverge exponentially, forward asymptotic PDF is multimodal. And this one, climate is stochastic and noise driven but quite linear, so actually I haven't had the time to tell you much about this, but in this case, although each trajectory is quite irregular, you know, they do decay back to the mean, that why they can be modeled by autoregressive processes. Forward asymptotic PDF is unimodal. Grand unification, again, I put the question mark because, you know, I don't take this too seriously. But anyhow, it's a way of thinking about things in a more unified way. So again, climate is deterministic plus stochastic as well as highly nonlinear. Internal variability and forcing to act strongly. Change and sensitivity refer to both mean and higher moments. So the convention as defined by successive assessment reports is the change refers essentially to the trend and to the sort of, and you know, variability to the natural stuff, although, well, it's more complicated than that. So this is, so concluding remarks 2, climate change. Okay, what do we know? It's getting warmer. We do contribute to it, so we should act as best we know and can. And as I said, I think, during my lecture, my first lecture on Monday, you know, God is in everything, but the devil is in the details, so as best we know and can. And the problem is not solved, as George has pointed out. You know, there are sufficient uncertainties. So what do we know less well? By how much is it getting warmer, and do we contribute to it? How does a climate system, atmosphere, ocean, ice, etc., really work? So again, you know, George pointed out a number of these uncertainties. There's one that I particularly like. You know, he mentioned the overturning circulation of the oceans, sometimes called the thermohaline circulation. Well, what do you think, you know, drives Wally Broca's conveyor belt? You know, make water sink in high latitudes and come up in low latitudes, at least in the present climate. Well, that's not really known. And I think, again, George hinted at that. To give you an idea, well, there's this thing about internal waves and various other things, but you know, just to give you an idea how little this is known, there's a paper that has been published by serious people, and you know, their criticism of it. But the answer is the fish, okay? Or the octopuses. It turns out that if you compute the quantity of kinetic energy put by living things of a certain size, obviously whales do more than you know, little snappers. If you compute that energy, it is about the energy that it takes to generate this motion. Okay? So when certain statements are being made, including on the sites of certain very respectable academies, that the problem has been solved, and now all we need to do is act on the knowledge that we all have, that is for the birds, whether they like ornithology or not. Right. Okay, so what to do? Well, better understand the systems, and the 4 things I told you, the power of understanding in making you believe in prediction. Explore the models and the systems' robustness and sensitivity. And again, I didn't really have the time to go into this, but instead of sort of Antonov and Pontryaghin's structural stability, you have to think about stochastic structural and statistical stability. And again, for those who know, you know, linear response theory, there's something called the response function, and its Fourier transform is a susceptibility function. And if you look at that, you will get an idea about how ENSO and other things like the MJO, the Madden-Julian oscillation, and so on, other cyclic phenomena might change in a different world. And here are some of the general references, and I thank you very much.